Thanks to Squarespace for sponsoring today's video.
Today we're going to look at the beautiful function which is the complex logarithm. So what I mean is we're going to take the logarithm of a complex number, or in general a complex variable. But in order to really get off the ground here, we first need to review the polar form of a complex number. So let's get a picture of the complex plane on the board. So this is my complex plane here. So this is the real axis in this direction, and this is the imaginary axis in this direction. So what I mean by that is if I take any complex number, I'll call it z, I can write it in rectangular form as x along the real axis, and then I times y along the imaginary axis. So here we have z is equal to x plus iy. So like I said, this is a rectangular representation of the complex number z, and it's a rectangular representation because you could think of this just as the coordinates in R2 of x comma y. But recall also that you can write every point in the real plane with polar coordinates. And so we should be able to translate that polar form in the plane into the complex plane. And in fact, we can. So let's get some parts of that on the board. So we'll draw a line segment that is from the origin to our complex number z. And then we'll make a measurement from the positive real axis to this line segment, and we'll call that angle theta. And then we'll make a measurement of distance from the origin to this point, and we'll call that r. Now, next up, what we'd like to do is find some sort of translation between r, theta, and x and y. And we can do that by completing this triangle right here. So let's complete this triangle. Notice that it has a base of x and a height of y. There we've got a right triangle, and then we can just do standard trigonometry. So notice that x is equal to r times the cosine of theta. That's because cosine of theta is adjacent over hypotenuse. Next up, y is equal to r times sine of theta. So that means we could re-express our complex number z as, let's see, r times the quantity cosine theta plus I times sine theta. So since I'm adding x plus iy, and both of them have a factor of r, I can factor that r out of the whole thing. But there's a very famous and beautiful formula called Euler's formula, which allows us to simplify this combination of cosine plus I sine in terms of a complex exponential. So this is like all over the internet. It's one of the most famous formulas on YouTube. And so that allows us to write this as, instead of r times cosine theta plus I sine theta, we can write it as r times e to the I theta. There's lots of reasons why this works. I think maybe the simplest one is to look at a series expansion of e to the I theta versus cosine theta and sine theta. And you'll see that you get equality of every term of that sequence. Okay, nice. So next up, it's probably important to notice that we have some periodicity in this picture. So if I, instead of measure from the real axis to this line segment just going around the circle a little bit, I can go around the circle the whole way and then make the measurement. In other words, I can do something like that. That has angle theta plus 2 pi, and that in fact gives me the same number. So I have this is also equal to r times e to the I theta plus 2 pi. And in fact, I can go around as many times as I want, either in the forward direction or the reverse direction, and I achieve the same complex number. So I can put an n here, and this n runs through all integers. So what that means is this polar representation of our complex number is not unique. Now that we've derived this formula, let's name some of these parts. So let's do it down here. So let's say we have z equals r times e to the I theta. And furthermore, we've taken theta between negative pi and positive pi. So we're able to do that because that'll cover the whole plane. So I will not include negative pi, but I will include positive pi. So including positive pi is like getting the negative real axis by going in this direction. In other words, by a positive 180 degrees. Whereas going negative 180 degrees, we can't quite do that because we're not including negative pi. So let's recall we had x was r cosine theta, y was r sine theta. So we can use the Pythagorean theorem to see that r squared is x squared plus I squared. But we'd like to give that another name, and that is the modulus of the complex number. So the modulus of the complex number is the square root of x squared plus y squared, which is equal to r. Next, we'll give theta a name as well. We'll call theta the argument of the complex number. So here I'll say theta is arg of z. And I'm very carefully putting a capital A here because putting a capital A here is like a little tricky notation to say that I'm going to take the value of theta between negative pi and pi, including pi but not including negative pi. So in fact, the argument with a lowercase is a multi-valued function. And in general, we would have lowercase arg is equal to uppercase arg of z plus 2 pi n, where n runs over all integers. So it's an infinitely valued function. Okay, and then maybe one more thing to note is that we see that the tangent of theta is equal to y over x. In other words, the imaginary part of the complex number divided by the real part of the complex number. So that means theta has to do with the inverse tangent function, but we really have to be careful about which quadrant we're in. So it's a bit dangerous to write that as the arctan. So now that we have all of these parts to define, we're ready to see what this complex logarithm actually does.
I've been using Squarespace for my personal academic website for several years, and I couldn't be happier with the experience. It's super easy to achieve a beautiful result using wonderful templates that allow for drag and drop design. Squarespace also makes it very straightforward to access the source code if you want further customization, like the LaTeX integration that you can see on my website. I'm currently on my annual summer rock climbing trip, and I've been using the Squarespace mobile app to check in on my site. This app is very well designed and not only allows you to check analytics, but also features website building tools in-app. Personally, I'm considering resurrecting my old climbing blog using this feature. So keep on the lookout for that. So what are you waiting for? Go check out squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/michaelpenn to save 10% off your first purchase of a website or a domain. And one more time, I'd like to thank Squarespace for sponsoring today's video.
Okay, so on the last board, we motivated the polar form of a complex number. I left the picture up here because it'll be useful for our calculation. So we have z equals r e to the I theta. R was the modulus of z, so that's the distance from the origin. And then theta was something that we call the principal branch of the argument of z, or the principal value of the argument of z. So it's the value between negative pi and pi. Okay, but notice using this setup here, it's very natural to take the logarithm. So we could take the log of z here, and that's going to give us the logarithm of r times e to the I theta. But then we can use some logarithm rules. So this is going to be the logarithm of r plus the logarithm of e to the I theta. But then we've just got a real number right here. And so if we've got a real number and we're taking the logarithm, that's just the standard natural logarithm. So I'll write this as the natural logarithm of, instead of r, I'll write the modulus of z, just to put it in terms of our complex variable z, so we can kind of extinguish the need for the reliance on the explicit polar form. Great. And then from here, I can use the fact that this log and this exponential cancel each other. So this gives us plus I times theta. But notice theta is the argument of the complex number. So we can write this as the natural log of the modulus of z plus I times the argument of z. But let's recall that this argument of z could take on infinitely many values, but that means this logarithm can also take on infinitely many values. So we have this principal value that's between negative pi and pi, but then we have like infinitely many more values that are multiples of 2 pi added on to that. Okay, so let's maybe bring this down here and note that we have the log of z is equal to the natural log of the modulus of z plus I times the argument of z. So that would be maybe the best way to think about this complex logarithm very, very simply. So now let's recall in the last board that we had a capital ARG of z, which gave us values between negative pi and pi. So we'd like to use that here, and that will create something called the principal branch of the logarithm, and we'll call that capital LOG of z. So that's going to be the natural log of the absolute value of z, and then plus I times this principal value of the argument of z. And the important thing here is this principal value of the argument of z is always between negative pi and pi. Okay, nice. So that gives us two nice things to think about when we're talking about the logarithm of a complex number. And we can actually link these two together pretty easily. Notice that this lowercase log is a multi-valued function related to this capital Log. It is in fact this capital Log of z plus I times 2 pi n, where n runs over all integers. So that gives us our infinitely many values of this function. Okay, so now that we've got this description of our logarithm, let's maybe save those over here, and then we'll work out some values of this logarithm and then look at some graphical properties. So far, we've defined the principal branch of the logarithm as follows. So we called it capital LOGZ, and we said it was equal to the natural log of the modulus of z plus I times the argument of z. And recall that the modulus of z was the distance of that point to the origin. So we could use the Pythagorean theorem or the distance formula to figure that out pretty easily. Next, this principal value of the argument of z always lied between negative pi and pi. So that's our choice. Another standard choice is to make it between 0 and 2 pi. And then the argument has the rule that if you evaluate the tangent of the argument of z, you get the imaginary part of z over the real part of z. Then we also had a multi-valued function related to the logarithm, which we called lowercase log of z. It was equal to this principal branch plus I times 2 pi n, where n was an integer. That's because the exponential function is 2 pi I periodic. Now we'd like to do some example values of this logarithm, and we'll do the principal branch, although notice that you can get all of the other values just by multiplying this I times 2 pi n on. Okay, so let's find the log of 2 times I first. So let's observe this is going to start out by being the natural log of 2, as 2 is the modulus of 2i. Then we have to figure out the argument of 2i. Maybe we should go over here and graph it. So 2i lives along the imaginary axis right here. So it's obviously 2 units from the origin, which we already encoded right here. And then the angle is pi over 2. And that's because the angle from the real axis or the positive real axis to the positive imaginary axis is 90 degrees, or pi over 2 radians. So since the argument is pi over 2, we have this as plus I times pi over 2. And that's our value of the logarithm of 2i. Maybe kind of as a little bonus right here, notice if we took the logarithm or the principal branch of the logarithm of I, we would get the natural log of 1, which is 0, plus I times pi over 2. So we would get something that's pure imaginary. So that's kind of nice. Now let's look at the log of minus 3i. So let's graph that. So that'll be down the imaginary axis 3 units. So that'll be like down here, minus 3i. And notice the argument in this case is minus pi over 2. You could either take minus pi over 2 or 3 pi over 2. But since we're taking our standard choice of argument to be on this range, we'll take minus pi over 2. So putting that together, we have the natural log of the modulus of this, but the modulus of negative 3i is just 3. And then we'll have minus I times pi over 2. Okay, nice. Now let's look at this next one, the log of 1 plus I. So let's get that in the picture. So 1 plus I is going to be about right here. So let's erase this pi over 2 so it's not in the way. So let's see, let's write that here. This is 1 plus I. So what's the modulus? Well, using the Pythagorean theorem on this triangle, we can see that the modulus is the square root of 2. And then you might say, what's the angle? Well, the angle is going to be something between negative pi and pi, so that when you take the tangent, you get the number 1. And so that'll be an angle of pi over 4. That's motivated by this definition of the argument over here. So putting that all together, we get the natural log of the square root of 2 plus I times pi over 4. We could simplify that if we wanted to 1/2 natural log of 2 plus I times pi over 4. And then for our next one, well, I'll change this kind of on the spot just so that it's a little bit easier to work with. Let's use the natural log of negative square root of 3 plus I. So where is that going to be? Well, let's see. Negative square root of 3 is going to be like a little bigger than negative 1 or a little smaller than negative 1. So that's like out here. And then plus I, that'll be right about here. So this will be our number that we're looking at now. So this will be negative square root of 3 plus I. Great. So now we need to make some measurements from there. Well, let's see. I think the angle from the positive imaginary axis will be pi over 3. So pi over 3 plus pi over 2 is 5 pi over 6. So the argument is 5 pi over 6. And then the modulus is 2 because it's the square root of 3 plus 1. So the square root of 4. So in the end, we get that this thing is the natural log of 2 plus I times 5 pi over 6, given that that angle is 5 pi over 6 like we talked about. Okay, so I think maybe you'll notice that in all of these calculations, we've stayed suspiciously away from the negative real axis. And there's actually a reason for that, and that's what we're going to get into next. So now, what happens on the negative real axis? So I've graphed our point -1 here, and what it seems like, so let's put that here. This is not what it is, but what it seems like is that the log, maybe the principal branch of the log of -1 should be equal to the natural log of the modulus, or the absolute value of -1, plus I times the argument. The argument here is most definitely pi, so maybe this should give us I pi. And if we weren't worried about this logarithm function being continuous, or like a fancier kind of beefed up version of continuity in the complex plane would be analytic, this would be totally okay. But in fact, we'd like to define a function that is continuous, and we'll see that this causes some sort of issue. And let's see what issue this causes. So let's think about an arc of a circle, which is approaching -1, but from 2 directions. So let's approach -1 from this direction and compare that to approaching -1 from this direction. And let's approach along a circle with radius 1. So that means right here it's going through the point I, and then down here it's going through the point -I. So if this function is continuous or well behaved, it should approach the same value. The logarithm should approach the same value regardless of which arc that we're approaching on. And that value should be probably I pi given our motivation over there. So let's maybe do this limit. So I'll maybe put a yellow box here to say that we're approaching along that arc. Well, that arc of the circle can be parameterized as follows. So the z values on that arc are e to the I theta. And here theta will be approaching pi from below. So I'll put pi minus to mean pi from below. So that's because here we start at theta equals 0. Here we've got theta equals pi over 2, theta equals 3 pi over 4, all the way up to theta equals pi. But we're coming from below. We don't care about what's happening from above. Okay, so let's see. We've got the limit as z approaches 1 of the log z along this branch, or along this arc of the circle, is the same thing as the limit as theta goes to pi from below of the log of e to the I theta. But that's going to be equal to the limit as theta goes to pi from below of I theta, which gives us I pi. So maybe let's put all of this in a big yellow box to show that, yeah, we're doing this along the yellow arc. So we get the limit as z approaches 1 along this yellow arc of the log of z is equal to I pi. And now let's go along the pink arc. So this is going to be as we approach from below, if you will, but it's really on the arc of that circle. So if we parameterize that, we have z equals e to the I theta again. It's still the unit circle, but now theta is going to approach negative pi from above. So here we're taking the parameterization of the circle from negative pi to positive pi. Now we'll take the limit as z approaches 1 along this arc of log z. So that's going to be the same thing as the limit as theta approaches negative pi from above of log of e to the I theta. But that'll end up being the limit as theta approaches negative pi from above of e to the I theta, but that gives me negative I times pi. So let's put a big pink box around this to show that that's what's happening along this pink arc. So just to reiterate, along the pink arc, the limit as z goes to 1 of log z is equal to minus I pi, but along the yellow arc, it's equal to I pi. So this is approaching minus I pi from this direction, and it's approaching I pi from this direction. So that tells us that at this point, -1, this principal branch of the logarithm is not continuous. And in fact, it's not going to be continuous at any value of the negative real axis, actually of the non-positive real axis, so we can't include 0 either. So that means we're going to restrict the domain of the logarithm to be the entire complex plane except for this non-positive real axis. So now that we've kind of thought through that, let's see where this logarithm sends this version of the what's called the slit complex plane, the complex plane with that removed. Let's see what its image is under this map. So we just got done motivating that our function, capital Log, the principal branch of the logarithm, could be defined to be a continuous, or actually more carefully an analytic, or more strongly an analytic function on the complex plane if we remove the non-positive real axis. So this space over here is something like c minus the interval from minus infinity up to 0, including 0. So this is sometimes called the slit complex plane. Now what we'd like to do is see what happens to some shapes over here as we map with this principal branch of the logarithm. So let's start by looking at what happens to the positive real axis. So let's see, if we take positive real numbers here, and take their complex logarithm, we'll notice that the argument is 0. So that's just the same thing as taking their natural log. But the natural log is onto, so it takes everything from the positive real axis and maps it onto the entire real axis. So that's just kind of standard knowledge from calculus. So to reiterate, this ray right here will map to the entire real axis over here. Great. And now maybe it would be sort of nice to see some points along this ray. Well, maybe this point 1 will get mapped to the origin 0. So that's pretty obvious because the natural log of 1 is 0. So that means everything between 0 and 1 gets mapped to the negative real axis, whereas everything between 1 and infinity gets mapped to the positive real axis. Okay, so next up, let's see what happens to the imaginary axis. So if we take the imaginary axis, so notice that's everything with an argument of pi over 2, but the modulus can be anything. So what kind of picture does that build? Well, notice the argument is constant at pi over 2, so the imaginary part of the logarithm is constant, whereas this portion is variable. So that'll give us a horizontal line up here that's at the level of I times pi over 2. Great. And that's in fact what any ray that starts at the origin or emanates from the origin maps to. So if we go down here, so that's got an argument of negative 3 pi over 4, so that'll map down here to a horizontal line with an imaginary part of negative 3 pi over 4 times I. And now looking at this kind of motivates what's happening to this dotted ray that we have to exclude. So it kind of simultaneously has an argument of negative pi and pi. So that corresponds to this horizontal line up here at I pi, and this horizontal line down here at negative I pi. So we don't get mapped onto those, but we do like almost get mapped onto those. So in fact, what's happening is we're taking this entire slit complex plane and we are mapping it to just this strip in the complex plane. Now let's see maybe what happens to one more type of shape, and that is a circle. So let's take a circle of radius r and see what happens to that. So notice in this case, the modulus is fixed at r, whereas the argument is varying. So if the modulus is fixed, that means the real part is always going to stay the same while the imaginary part varies. That's going to give us a vertical line, but not exactly the entire vertical line, just the vertical line segment, open line segment between those 2 points. So maybe we would go over here. This would be the point natural log of r. And then we've got this open line segment from here up to here. And then you could vary the radius and you would get different line segments either going further out that way or further back this way. For instance, a circle that has a radius which is less than 1 would be mapped to something which is situated over here to the left of the imaginary axis. So it would look something like this. And now from here you might think, well, this is just the principal value of the logarithm. Is there anything that we can do with the multi-valued function to maybe make this thing a little bit nicer? What I mean by nicer is that we don't have to maybe cut out part of the complex axis or the complex plane here. And maybe could we make it an onto function over there instead of just onto this strip? There's actually a technique for doing this, and that technique is really beautiful. So what you want to think about is having infinitely many complex planes, and those infinitely many complex planes are connected to different values of this logarithm. So the principal branch will be connected to one of the complex planes, and then you'll have these planes connected to all of the values of the integers. And then for each of these complex planes, you want to cut a slit in them. That's like cutting out the negative real axis or the non-positive real axis. And then you'll want to glue all of these slits together so that you can transition from one plane to the next. Okay, so let's maybe get a picture of what happens to the values in that case. Now we'd like to patch together some of the multi-valuedness of the logarithm function. Let's recall that lowercase log was capital Log plus I times 2 pi n, where n was an integer. So here I've looked at a couple of branches. Obviously there are infinitely many branches as there are infinitely many integers, so there's only room to do so much. So we have the principal branch here, and then the branch log of z, or log of z, plus I 2 pi. So that'll be the case when n is equal to 1. And then here's the case when n is equal to -1. So let's recall from what we saw on the last board, this principal branch takes this slit complex plane. So in other words, the complex plane with the non-positive real axis removed, and it maps it over here to this strip between -I pi and +I pi. Okay, now what happens up here? Well, we essentially just move this strip up 2 pi units because we're adding 2 pi I. So that's going to take this version of the strip and it's going to map it over here, or that version of the slit complex plane, and it's going to map it right here. Okay. And then finally, if we subtract 2 pi I, that's going to shift it down. So that's going to take this version of the slit complex plane over here and map it down to this strip. Great. So now if you glue all of these things together, you get something called the Riemann surface for the complex plane. And that actually has a pretty interesting property. So you kind of have to look at this in time. But if we start right here and we loop around this slit complex plane in this direction, then we'll come out the end and loop around this one. That's how they're glued together. And then we'll come around the end and loop around this one. So the path is going up this sequence of complex planes. And over here, the picture would look like this straight vertical line going through all of them as follows. Okay, that's a good place to stop.